On May 4, 2026, a small aircraft departing from Pampula Airport in Belo Horizonte suddenly lost altitude within minutes of leaving the runway. The plane collided with a three-story residential structure in the Silveira neighborhood. The aircraft struck the stairwell of the building, sparing the residents inside, but the crash highlighted a terrifying reality of aviation. The flight crew had only seconds to realize something was catastrophically wrong before impact. This incident is not an anomaly. It is part of a relentless pattern that aviation investigators have tracked for decades. The most dangerous moment of any flight is not cruising at 30,000 ft. It is the initial climb, when aircraft are heavy with fuel, flying at their slowest speeds, and operating closest to the ground. A mechanical failure leaves almost zero margin for error. Boeing's statistical summary of commercial jet airplane accidents reveals a disturbing truth. While the takeoff and initial climb phases represent roughly 2% of a standard flight's total time, they account for approximately 13% of all fatal aviation accidents. These are not random events or unexplainable mysteries. There is a systematic vulnerability during those critical first minutes after the landing gear leaves the tarmac. The physics of takeoff create a high-stakes balancing act that aerospace engineers refer to as a highly controlled emergency. Aircraft need maximum engine thrust to lift heavy fuel loads and passenger cabins, which places extreme stress on mechanical components operating at their absolute thermal and rotational limits. Concurrently, they require maximum lift from the wings. But the slow speeds immediately following liftoff provide significantly less aerodynamic stability than the high speeds achieved at cruising altitude. To manage this, pilots calculate 3 critical V-speeds before every departure. V1 is the decision speed. Once the aircraft exceeds this speed, the takeoff must continue even if an engine fails, because there is no longer enough runway to stop safely. VR is the rotation speed, where the pilot pulls back on the yoke to lift the nose. V2 is the takeoff safety speed, the minimum speed required to safely climb with one inoperable engine. If a system fails in this narrow margin, physics dictates the outcome. The Belo Horizonte crash represents a textbook low-altitude emergency. Preliminary reports from Brazil's Aviation Accident Investigation Board, CINEPA, point toward a critical loss of altitude and power while still within sight of the airport. What is particularly unsettling about these crashes is how rapidly they unfold. Unlike emergencies at cruising altitude, where pilots might have 20 to 30 minutes to diagnose problems, consult manuals, and run through detailed checklists, takeoff emergencies develop in seconds. Flight crews often have less than a minute to process the failure, leaving virtually no time for troubleshooting. To understand how quickly weather and physics can overwhelm an aircraft during departure, consider the tragic case of Air Florida Flight 90 in January 1982. The Boeing 737 was departing Washington National Airport during a severe snowstorm. Ice had accumulated on the wings, degrading their ability to generate lift. More critically, ice had frozen the engine pressure ratio, or EPR sensors. When the pilots advanced the throttles, the frozen sensors fed false information to the cockpit instruments, indicating the engines were providing maximum takeoff thrust when they were actually operating at a much lower power setting. The cockpit voice recorder captured the first officer noticing the anomaly during the takeoff roll, stating that the instrument readings did not match the actual acceleration. However, the captain elected to continue past Vone. The aircraft lifted off, but without adequate thrust and heavily burdened by ice, it entered an aerodynamic stall just seconds later. It crashed into the 14th Street Bridge over the Toke River, killing 78 people. The NTSB investigation revealed that the crew had barely 30 seconds from liftoff to impact. There was no time to diagnose the frozen sensors. This unforgiving dynamic repeats across decades of accident investigations, even when weather is perfectly clear. American Airlines Flight 587 departed John F. Kennedy Airport in November 2001. The Airbus A300 was in its initial climb, heavily loaded with fuel for a flight to the Dominican Republic, when it encountered severe wake turbulence from a preceding Japan Airlines Boeing 747. Reacting to the sudden roll caused by the turbulence, the first officer responded with aggressive alternating inputs to the rudder pedals. The aircraft crashed into a residential area in Bell Harbor, Queens, killing all 260 people on board, plus 5 people on the ground. The entire event, from the first turbulence encounter to the catastrophic structural failure, lasted less than 20 seconds. The NTSB investigation revealed a crucial misunderstanding of low-altitude aircraft limitations. The first officer's alternating rudder inputs exceeded the aircraft's ultimate structural load limits during the high-stress takeoff phase, causing the entire vertical stabilizer to snap off the tail. At higher speeds and cruising altitudes, aircraft computer systems and aerodynamic forces naturally limit the physical travel of the rudder to prevent this exact kind of structural overload. But during the initial climb at a relatively low airspeed, those extreme inputs proved catastrophic. The pilot had been trained in a specific upset recovery program that incorrectly emphasized aggressive rudder use. Training that, when applied in the vulnerable takeoff window, doomed the flight. Configuration errors during takeoff create equally deadly scenarios, proving that human factors are just as critical as mechanical ones. When Northwest Airlines Flight 255 attempted to depart Detroit in August 1987, a series of cockpit distractions led to a fatal checklist omission. The crew failed to extend the wing flaps and slats. The McDonnell Douglas MD-82 had sufficient engine thrust to accelerate down the runway and lift off briefly. However, without the additional aerodynamic lift generated by the extended flaps, the wings simply could not maintain flight at that speed. Compounding the error, the aircraft's takeoff warning system, or TOWS, designed specifically to sound an alarm if the throttles are advanced without the flaps extended, failed to activate due to an electrical malfunction. The aircraft climbed to approximately 50 ft before stalling, rolling violently, and crashing near the airport perimeter. 154 people perished. 21 years later, in August 2008, Span Air Flight 5022 suffered the exact same fate in Madrid. Another failed TWS alarm and another catastrophic stall immediately after liftoff that claimed 154 lives. Takeoff emergencies often begin with aircraft that appear to be operating normally. Engines produce thrust, the aircraft accelerates past VONE, and the wheels leave the ground. The crew experiences a standard departure profile until a latent aerodynamic or mechanical failure suddenly manifests, leaving them suspended between the runway and the sky. The psychological load on pilots facing these emergencies is immense. This is known in aviation psychology as the startle effect, the delay in cognitive processing that occurs when a sudden life-threatening emergency interrupts a routine procedure. The Federal Aviation Administration and global safety boards focus heavily on mitigating risks during the critical phase of flight. Modern commercial aircraft now feature highly sophisticated automated flight envelopes. Fly-by-wire control systems actively prevent pilots from inadvertently exceeding structural limitations or stalling the aircraft, effectively rewriting the rules that doomed flights in the past. Survival depends entirely on engineering, training, and physics working exactly as designed. Until aerospace technology can rewrite gravity, the initial climb will remain aviation's most perilous frontier.